Hello, and welcome to this video of the series Basics of Linear Algebra for Quantum Mechanics. In this video, we will deal with the relevant matrix calculation and why it is important. Matrices are used to manipulate vectors, and what you can manipulate in the vector: the magnitude, the direction, the dimension, which is also represented by number of elements. For example, if you look at in this case, we have an old vector which is of dimension 2, number of rows as 2 and column as 1, having element 2, 2. You multiply it with a given matrices, and you will see a new vector which has same dimension, 2 rows and 1 column, but it has the elements 1 and 1. So the magnitude now has been altered. You can also do series of mathematical operations with matrices, for example, matrix addition, and how it is performed. One of the most important criteria for matrix addition is that the vectors that has been applied to should have the same dimensions, which means the number of columns in the first vector or matrix should equal to number of rows in the second. That will help you to add the elements. You can also multiply a matrix with a scalar such that the scalar value is multiplied by all the elements of the given matrices. The subscript A11, A12 here means the matrix indices. So they do not represent the number, but the place of that element in the matrix. You can also multiply the matrix. Again, the condition is that the number of columns in the first one should be equal to number of rows. So here if you see, the number of columns in the first one is 3, the number of rows in the second one is 3, they are matching, and you can then multiply this matrix element by element. One of the important concepts is transposition, which is denoted by notation raised to the power t. And how this is achieved is by converting the rows in a given matrix into columns and then taking the complex conjugate of that. The terminology in quantum mechanics is denoted by A, the symbol sign of a cross instead of AT, and same for in the complex number case, it's represented by bar over the complex vector. So for example, z is equal to a plus bi has a complex conjugate, which is z bar represented by a minus bi. And in the previous video, we have explained how to calculate the conjugate of the complex number. It represents the mirror image. Transposition, for example, of the L2 norm vectors can be achieved by what we have defined, that taking a vector, transposing it, and then taking a complex conjugate. And if you multiply the transpose with the original vector, it preserves the norm. Extending the definition further, we have square matrices where we have the same number of rows as columns, and you can multiply it with any matrices. Again, remember the rule. Will hold the dimensions of the matrix that it is multiplied with. For example, here A is multiplied by V holding the dimensions of B. The number of rows is 2 and the number of columns is 1. We also have Hermitian matrices. They are if the transpose of a matrix is equal to the matrix itself. This will help also in terms of the mirror imaging of what we see in the transposition of complex matrices. So here, given a matrix A, if you transpose it, calculate the conjugate, you will still get the matrix A. So this represents as Hermitian matrices. You also have identity matrices of different dimension, where all the diagonal elements are 1 and rest are 0. So for example, you see dimension n into n, and n could be any number. For example, 2 by 2 matrices, diagonal elements are 1, 1 and others are 0. An identity matrices preserves the matrix vector it's multiplied with. Extending the concept of identity matrices to unitary matrices. So identity matrices, we know what it is. And unitary matrices is something that if a matrix is multiplied with the transpose of its own, it results into identity matrices where the diagonal elements are 1 and all other elements are 0, then that particular matrix is called unitary matrices. It is important to know that applying a unitary matrices to vector, for example, we see the example of initial vector, we applied a unitary matrices A, and what is the final vector? It helps us to retain the magnitude. So both the magnitude of the initial vector and the final vector after applying the unitary matrices remains as under root of 8. And you can solve it further, but the value still remains the same. To understand this in a more Venn diagramish kind of thing, so we have the matrices, square matrices classes, we have the square matrices, we have Hermitian, we have unitary, and Hermitian and unitary are overlapping with the identity matrices as we have seen in the definition of the unitary matrices. So this is for the matrix calculus, which is very, very important for manipulating the vector, as I said at the beginning of the video. And these concepts are important to keep in mind because they will help you further define some of the physical properties that we're gonna see in quantum mechanics. I'll stop here and I'll hope to see you in next video. Thank you very much.